So welcome everyone to what I think is now the fifth UK CMIP6 analysis workshop, and we've got 5 presentations today. As we did before, each presentation will have 8 minutes, and Hazel will give the presenters a quick reminder when they've got 2 minutes to go. If you have questions, please type them into the chat, and then at the end of each presentation we'll have a couple of minutes where I will try and summarize some of the questions for the presenter. And if there's extra questions left over, there are Google Docs available. Please put the comments and questions into there, and then the presenters can look at the Google Docs and follow up with you afterwards. I think that's everything we need. Your mics are almost certainly muted by Poppy, so I suggest we kick off. And first up is Stephen Turnock from the Med Office Hadley Centre. Steve, are you ready to roll?
Yeah, I think so, yeah.
Okay, then I'm going to hand over to you and mute myself.
Okay, hi everyone. So yeah, thanks for joining, talking about this. So I'm going to talk about some of the work I have been doing looking at air pollutants in the CMIP6 models and scenarios like that. So this work sort of started out to try and understand what these latest generations of system models and chemistry climate models are projecting into the future in the numerous different scenarios that are available now onto the CMIP6 pathways. So obviously air pollutants are quite important for human health, ecosystems and climate, and we wanted to understand what are these different projections of these different future scenarios telling us about, in particular, particulate matter and ozone at the surface in the different models. So on this first slide here, I'm just showing the global air pollutant emission pathways across the different CMIP6 scenarios. So what's important here in this generation of scenarios is there's a lot more variety than there was in CMIP5. So it gives us a chance to understand a lot of different trajectories from both the SSP1s and SSP2s, where the sort of high mitigation scenarios in terms of air pollution emissions and also climate change mitigation, to the SSP370 and SSP585, which is very low mitigation in terms of air pollutants and their trajectories into the future. So obviously an important one is here in SO2, which is precursor for aerosols in the atmosphere. And as you can see, the red line, this is the SSP3 scenario, the low mitigation pathway, which shows quite low levels of reduction out into the future. Whereas if you go to these blue and green pathways, you can see really high and fast mitigation measures that are applied to SO2. And you can see similar sort of trajectories for the different air pollutants. So NOx as well, which is an ozone precursor in the atmosphere. You can see that the SSP5 and 370 pathway don't really change much from present day in the emissions, which is this dotted line, and turns to the high mitigation scenarios, which change very quickly and rapidly. And methane concentration change is a particularly interesting one as a tropospheric ozone precursor. And as you can see, there's quite high trajectories in quite a number of pathways here, and it's only the really high mitigation measures that really aggressively attack and reduce methane concentrations into the future. So that's sort of an introduction to it. So one of the first things we wanted to do now, hopefully moving to the second slide, is to try and look at these models in a present day configuration and see how well are they performing against some of the surface observation data sets that have been collated recently. So on the left here, this is surface ozone from 5 CMIP6 models that were made available at the time of this work. And these top 2 panels are December, January, February means, and the bottom 2 are June, July, and August. And this is showing the diversity in the model response in these 10-year climatologies in surface ozone. So we can see a lot of model diversity occurs in sort of continental northern hemisphere regions in this sort of winter time period, but there's a bit more agreement in the summertime period here. But comparing to this observation, so this is the bias from the models against the observations from this, there's a TOR database called, shows that the models all tend to overpredict ozone in the lower levels of the model. So this is assumed to be the surface here. So we have too much ozone at the surface in all the CMIP6 models in both seasons. So that's something that's going to be investigated further, why the models are still doing this. And this is a common feature that's been seen for models from different generations as well. So on the right is looking at PM2.5 or particulate matter less than 2.5 microns in diameter. And again, we have 10 models from the CMIP6 database here for this. And again, we have similar model diversity panels here on the left-hand side, which shows that a lot of them are natural source regions. So see the Sahara dust region comes out, showing lots of different model diversities here, and lots of uncertainty about how different models are treating dust there. And there's some of about the high anthropogenic emission areas of sort of the Indo-Gangetic Plain and East Asia towards China. And again, the overriding feature when we compare these to some of the surface observations we have for PM2.5 over this period, which are remote from urban areas for these large sort of global chemistry climate models or Earth system models, that they all tend to underpredict the level of PM2.5 at the surface here. So that's a common feature again, which is probably due to a number of reasons which are under investigation as well, which I won't go into at the moment here. So then taking that forward, we want to look at what do the future scenarios now, what do the models say projecting out into the future. So on the left hand side, this is the annual mean change from present day, which is taken to 2015, the CMIP6 scenarios. We have sort of 5 main scenarios here, which had a lot of most data for at the time of writing this. So this is change in surface ozone over all these different regions. So we have Northern Hemisphere regions at the top, sort of tropical regions, and Southern Hemisphere type regions at the bottom, and then the global change. So really what to look at for here is the sort of low mitigation scenarios, this SSP3 and SSP585 in the reds colours, that they show in these scenarios over most regions that ozone is and the surface is projected to increase over these regions into the future. Whereas if you look at the high mitigation for both climate and air pollutants in this blue line, you can see there's a reduction over most regions as well. So this is trying to tell us the different scenarios of what we're following and what kind of trajectories are important to consider and what kind of emission reductions we want to look at and what kind of benefit extra you get from climate as well. So, and again, the model diversity showing in the shading, hopefully it's come out here, and some regions have much more uncertainty in the different model responses than others, which they tend to agree much more on. And so on the right panel now, moving on, so this is looking at one scenario in particular, the SSP370, because we had more data for that. And this is looking at 2050 in the time period, and looking at regions here and how they've changed in 4 different models here to try and understand why are the models differently over different regions. So I've highlighted 2 regions of particular interest in South Asia, where 2 models here are showing a smaller increase in surface ozone in this scenario than other 2 models which show quite a bit larger increase. And again, for East Asia, there's a bit of diversity among the models, and you can see that through all the different regions. So going forward is trying to understand, why do these models do different predictions into the future? What is it about their chemistry, their meteorology? Because they should have been fed by the same anthropogenic emissions into the future. So it's understanding why they're showing differences here in these responses like that going forward. And again, you can pick different regions to understand why different way regions are understanding differently. So again, if you look at more natural regions, maybe they agree more, or some models do different things, or anthropogenic dominated regions and the chemistry takes over in different responses. So just to move on quickly to the last of the slides now. So this is now looking at the same sort of setup and slide for PM2.5 here. So quite a different response in that a lot of these scenarios that of the 4 we've considered here, that they are reducing into the future over most regions. So aerosols has been targeted as something that to reduce for human health regions. So a lot of SO2 is going down consistently across most regions, and you can see the response is the same in most scenarios in the future. So these are being tackled for human health regions as well as climate mitigation in some aspects going forward. However, some of the regions, particularly the South Asia, which is mainly in India, there's a lot of uncertainty about how the different emission trajectories are going to go in these regions in the future. So again, there's a lot of uncertainty and much more diversity, particularly on the short term, about how this region might respond to changes in emissions and changes in climate and their PM2.5 response. So again, and particularly comes out here are some of the more natural dominated regions such as South America, Southern Africa, and Southeast Asia, where you can see the spread in the model responses become a bit more larger, particularly for the SSP370 scenario. And again, this could be due to how the models treat natural emission sources of aerosols over these regions. So again, this figure on the right is showing 4 individual models in 2050 and their response from present day in this SSP370 scenario. And again, I just wanted to highlight these more 2 naturally dominated regions in terms of aerosol response. And you can sort of see, well, I think I've messed up my boxes, I realized before, but anyway, some models predicting it. Okay, yeah, thank you. There's an increase in some regions here, but also a decrease in others. So it's interesting to see how some of these regions and these models respond in different regions because of either climate or natural emissions or projections going forward. So, and again, you can pick a particular region of interest and try and understand what the model is doing differently across those regions. So then there's more work to go into this to try and understand the drivers of these changes and what's happening in between the different models. So some of the future work that I'm going to be doing is trying to understand these changes and why the models are projecting differently. Is it something to do with how they parameterize different processes, or what's included? Again, anthropogenic emissions should be similar, and greenhouse gas pathways should be similar in each scenario. So they're responding different ways to different things, and trying to understand some of this model diversity, which is quite important in understanding how these air pollutants and composition is projected into the future in these models. So that was all I had on those 4 slides. So I think I've stayed within time.
Okay, thanks, Steve. While there's some things coming to the chat, I'll start things off. So early on, can you hear me okay, I should say, to begin with?
Yeah, I can hear you, Colin, yep.
Yep. So in one of your early slides, you mentioned that there was a systematic overestimate in tropospheric or near-surface ozone. Can you give an indication what the sort of relative magnitude of that is compared to either the observed values? And then if you've got some idea what's causing that, that would be interesting to hear as well.
Yeah, okay, so I'll just go back to this slide. So again, these are just absolute values. So you can see that at the surface, where, obviously it varies over different regions, but we're, looking at terms of more than 5 ppb bias in some seasons, and even worse in summer. So yeah, this is a common thing that's been seen in a lot of not only global models, but regional models on scale, and trying to predict lower level surface ozone. And I think in different models they have different issues, and I think in the UK model particularly, obviously you have a lot of model levels near the surface, and it's maybe something to do with mixing of emissions, and there's maybe too much emissions at the surface which can destroy too much ozone or form too much ozone. So I think there's a thing for mixing there, and probably emissions and resolution. So it's very difficult to use these global scale models to try and represent point sources. I know it's a particular issue, and there's different ways to try and get around that. So yeah, it is a common thing that people get wrong. But looking at individual sites which are more remote, rather than these sort of broad brushes, that some of the seasonal signals and seasonal trends, the models do tend to pick up quite well. So there's probably just a question of maybe too much ozone in the lower levels, which is something to figure out.
Can you just give an indication of the size of that bias, which is of order, let's say 8 to 10 ppb? What is the observed DGF and JJA amounts of ozone for non-experts? So we talking 10% error, or?
Depends on the region, because obviously some in the season, but yeah, so in ozone tends to be lower in some of there, so yeah, probably a higher percentage, yeah, probably more than 10% maybe at times. But in ozone in summer, it's, yeah, I guess it's probably about 20%, maybe 10 to 20% probably.
Okay. And then you mentioned a number of the SSPs, and in particular, I think for air quality, SSP37, and then the SSP37 low NTCF, which is near-term climate forces. So that one was designed, I think, specifically to investigate potential co-benefits between near-term climate mitigation and air quality. Is that right? Mm-hmm. And is there anything that's coming out of the comparison of SSP37 against its low NTCF equivalent?
Yeah, so I didn't do a lot of work because there was a companion bit of work done by someone else looking at the differences, particularly in terms of air quality response, but also climate response as well between these scenarios. So I haven't really included much detail on that. So there's a separate paper in discussions at the moment on that. So yeah, so you can sort of see some of the differences here, where this dashed line is the low near-term climate force of response scenario, and that's companion to the solid red line. So essentially they're following the same greenhouse gas climate pathway, but the air pollutant emissions have been drastically reduced to the levels of almost the SSP 126 level. So just picking up, let's pick up Europe since we're in it. You can see the difference between the solid red line and the dashed one there. So with these extra cuts or dramatically reducing emissions, you can reduce the surface ozone impact to virtually the same as present day, rather than having, a 3 to 4 ppb increase regionally. So it's those kind of things you can sort of eliminate the air quality penalty from this scenario by doing these dramatic emission reductions, but not touching the climate. So it's those kind of things that, yeah, you can see from other regions there's a dramatic reduction and a difference between those scenarios. So yeah, there is work going on to look at that and the difference between those two scenarios. And as I said in this companion paper, they have looked at things as well, like number of dry days, number of wet days, precipitation, temperature changes. And again, some of those aren't significantly different between the two scenarios, but in terms of the air quality aspects like this, you do see a significant difference as well. So you can get immediate benefits from that kind of a scenario. Yeah, so it's going forward, and there's a lot more in the CMIP program where it's been looking at these different fixed emissions like low methane, low ozone, low aerosols, and you can try and isolate the different signals in there as well.
Okay, great. Right. Many thanks, Steve. So if there's any more comments or questions, please put them in the Google Doc, which is available, the link on the side. So we'll move to the next presenter now. Thank you, Stephen. The next is Jonathan Beverley, University of Exeter, who is going to tell us about ENSO teleconnections. So over to you, Jonathan, and Hazel will tell you when you have 2 minutes to go.
Yeah, thanks. Can you hear me?
Yes, I can hear you fine. Yeah.
Excellent. Yeah, so I'm going to be talking today about my work, which I'm doing at the moment, which is looking at future changes to teleconnections, specifically those associated with El Nino over the North Pacific and North America. And this is work that I'm doing with Matt, Hugo, and Rob in Exeter. So in the present day, El Nino has a major impact on the weather and climate of North America. So this plot here shows the surface temperature and 850 hectopascal wind anomalies associated with El Nino years in the ERA 5 reanalysis data set. And you can see that there's in El Nino years, you have an anomalously depollution low, and this cyclonic circulation here acts to advect warmer air across much of North America, resulting in these positive temperature anomalies across much of the North American continent. So as El Nino has quite an important impact on the weather in North America, it's therefore important to understand how the teleconnection may change in the future. So to do this, we use data from 17 CMIP6 models. So we use 450 years of data from the pre-industrial control, which has CO2 concentration set to represent conditions in 1850. And then we also use 75 years of data from the abrupt 4 times CO2 simulations, in which the CO2 concentrations are abruptly quadrupled from the 1850 value. Focus on Northern Hemisphere winter, so December, January, and February. And we define an El Nino year such that if the Nino 3.4 index exceeds 1 standard deviation of the control Nino 3.4 index time series, that year would be an El Nino year. So first of all, looking at this teleconnection in the control multi-model mean, which is what's shown in the top left panel here, we can see that this looks a lot like the equivalent from ERA 5. So in El Nino years, we have an anomaly depollution low, positive temperature anomalies across much of northern North America. However, when we look at the equivalent in the abrupt 4 times CO2 simulations, this is again the multi-model mean, we notice 2 things principally. The first is that the anomalous low pressure is shifted to the east, and this is associated with an eastward shift of El Nino precipitation, as the eastern Pacific is expected to warm faster than the West Pacific, which reduces the barrier to convection and results in an overall eastward shift in El Nino rainfall and the associated teleconnection patterns. The second thing to notice is that the temperature anomalies in El Nino years are much weaker across almost all of North America. And this is partly associated with the eastward shift of the circulation anomalies, but also a weakening of the circulation anomalies and the anomalous low pressure in some models. And what we show on the right here is the regression of the surface temperature against 850 hectopascal meridional wind averaged in this box here for the control and abrupt 4 times CO2. And while this relationship does get slightly weaker in the future, it still suggests that the wind anomalies over the North Pacific are the main driver of the temperature anomalies over northern North America. So to investigate this further, these plots on the left here show the relationship between between the temperature anomalies over North America and the meridional wind anomalies over the North Pacific. So on the x-axis here, this is the average meridional wind anomaly in El Nino years averaged over this North Pacific box. So this is the same box as used on the previous slide. And on the y-axis is the temperature averaged over this North America box. So this is kind of centered over that area of positive temperature anomalies that we see in El Nino years. And this is a control on top and abrupt 4 times CO2 on the bottom for all 17 CMIP6 models. And we see that the magnitude of the temperature anomalies over North America is closely related to the strength of the wind anomalies over the North Pacific in almost all models. So there are a few outliers in the control, but by and large, a stronger wind anomaly over this North Pacific region is associated with higher positive temperature anomalies over North America. And this is also true in the control, in the abrupt 4 times CO2, where we see that there's a strong linear relationship between these variables. And this is also the case when looking at the difference between abrupt 4 times CO2 and the control, which is what's shown in the middle here. So this time we're looking at the abrupt 4 times CO2 minus control wind anomalies on the x-axis and abrupt 4 times CO2 minus control temperature anomalies on the y-axis. And again, we see that there's a strong linear relationship between these, which further suggests that it's changes to the El Nino circulation anomalies that are the dominant cause of the change in temperature anomalies over North America, rather than other factors such as changes to the equator to pole temperature gradient, for example, where we expect the high latitudes to warm faster than the low latitudes. So we've seen that the weaker El Nino temperature anomalies in abrupt 4 times CO2 are partly related to the shift in circulation anomalies, but also a lot of models show a weakening of the circulation anomalies and the anomalous low pressure as well. So we've had a look at what possible causes of this might be. So these plots here show the divergence anomalies associated with El Nino at 200 hectopascals and multiplied by the Coriolis parameter. So this is the rough indicator of the Rossby wave source. And if you look at the equatorial Pacific region here in the control, this area of divergence here is associated with the El Nino precipitation. And in the future, as well as shifting eastwards, precipitation associated with El Nino is generally projected to increase in the equatorial Pacific. However, despite this, you'll see that in the abrupt 4 times CO2 simulations, while it does shift eastwards as expected, it's also weaker at 200 hectopascals than in the control, which could result in weaker Rossby wave propagation from the equatorial Pacific to North America. However, in a warmer world, we also expect the tropopore's height to increase. So the main divergence may simply be occurring at high levels in the atmosphere. So to try and investigate this further, the work I'm doing at the moment involves using a barotropic model with a combination of different forcings and basic states to see what the impact of changing only the forcing or changing only the basic state has on the teleconnection to North America. For example, using the control forcing on the abrupt 4 times CO2 basic state. And hopefully by using different forcings and basic states from individual CMIP6 models in this way, this may also give some insight into the causes of the diversity and the teleconnection response among the CMIP6 models, particularly the abrupt 4 times CO2 simulations, which tend to have a larger spread than in the control.
2 minutes.
That's all I'm done, thanks.
Okay, many thanks, Jonathan. While some people are putting things into the chat, hopefully I'll start off. So you mentioned through the presentation that the location of ENSO shifts eastwards. So there has been this sort of discussion, I think, that the character of ENSO may change in going into the future from what might be typically called East Pacific ENSOs to sort of more Central Pacific or Modoki type ENSO. Yeah. So does that mean you need to have some kind of shifting time varying metric for finding these ENSOs as you go into the future to capture them correctly?
I'm not sure whether that's so much of an issue when it comes to looking at the SSTs, because I'm more for defining these El Niños, I'm always looking at the Niño 3.4 index, and I think the SSTs, I think they're less. I think that region is still fairly representative of a future El Nino event as well. And I think the teleconnections North America is in the present day at least, it's kind of less sensitive to the shift of the difference between Central Pacific and East Pacific El Nino.
Okay, and I know you've been primarily looking at, let's say, North America, but I can see with the figure that's on the screen now that in the 4 times CO2 runs, there's still a very clear signature over the Gulf of Mexico. So is there any intention to consider changing ENSO impacts on hurricanes in the Atlantic, which we know there's a strong impact of ENSO on those features?
That's not something that I've considered yet, but it certainly is something that could be looked at down the line. Just for the time being, I've just been focusing on on this North Pacific and like North America teleconnection. But yeah, that's certainly something that could be looked at, I guess. Yeah.
Okay, and I guess associated with that, the other part of the North American link to El Nino is sort of California/Southwest USA rainfall variability. So is that something that's there's a signature on or not?
So I haven't spent a great deal of time looking at precipitation response yet. I think that's typically slightly weaker than the temperature response over North America. But yeah, that's something that it would definitely be good to look at, because yeah, it does have, as you say, has a big impact on the rainfall in California region. And I think certainly in the temperature in kind of south, because you also have the temperature teleconnection to southeast USA, and I think that also showed a weakening across the majority of models as well.
Okay, I'll ask the last question as soon as I'm asking them. So teleconnections from ENSO are quite sensitive to atmospheric model resolution. So I don't know whether the high-res MIP group of models actually made 4 times CO2 experiments, but would it be interesting to actually try and, let's say, categorize the response as a function of atmospheric model resolution?
Yeah, that is again, that's something that I've thought about, because yeah, as you say, it would be quite interesting to look at kind of what impact the resolution does have on these events. As you say, I'm not sure whether there is an abrupt 4 times CO2 high-res MIP, but if there is, if there is, then yeah, that would be worthwhile looking at some point, hopefully, if I can find the time.
Okay, great. Thanks a lot. If there are any more comments, please put them in the Google Doc. We'll go to the next presenter, Richard Wood from Met Office Hadley Centre, who's going to tell us about understanding the historical simulation in UK models. Over to you, Richard.
Okay, great. Thanks. Thanks. Hi, everybody. So this is a talk without so much conclusions, but more the conclusion is a hypothesis more. So, but the objective really is to understand some of the features, some of the kind of really broad features of the historical simulations in the UK model. And I should say right at the start that really this builds on a number of pieces of recent work by particularly Jonathan Gregory and Tim Andrews and others, which was completely news to me. But so thanks to them for really kind of bringing me up to speed with some recent developments, which I'll show you shortly. This is just been this is written up now just in this paper by Martin Andrews, which is a kind of overview of the historical runs of the GC 3.1 runs, which has just been accepted in James. So if you look at the left-hand side, this shows the global mean surface temperature in the historical runs. So it's blue is the GC 3.1 low resolution model, and black is the corresponding observations. And I should say that the analysis is based on the GC31 LL model, but we think basically the same thing is going on in both the higher resolution GC model and in UK ESM. So the features that, I mean, it's it's sort of good news and bad news. I mean, the overall warming over the whole historical period is not badly reproduced, but there are some important features that don't look like the observations that we just wanted to understand. And this is a kind of really just a first step towards that. So first of all, you can see this early 20th century warming, which doesn't appear to be completely captured by the model. Then between about 1950 and 1980, there's a slight cooling in the observations, but there's a rather greater cooling in the model. And then finally, this very strong warming since about 1980, which is much stronger than we see in the observations. So the idea is just to get some hypotheses really about what's going on here. And so I've used this really simple energy balance model framework. So this is basically, this is an energy balance model with a fixed depth mixed layer. So what we're relating to here, so T is the global mean temperature anomalies, then N is the top of the atmosphere heat flux, and in the context of this, this is where the d temperature by dt term sits. So with a fixed depth mixed layer, this is just d by dt of the mixed layer temperature. That's the top of the atmosphere heat flux. Then we've got some kind of effective radiative forcing, which is the radiative perturbation after some really fast atmospheric adjustments have taken place. And then there's a kind of feedback term with this climate feedback parameter, which represents slightly longer term longer time scale climate feedbacks on the temperature. So this model is quite good for timescales that are long enough for the mixed layer to come into equilibrium, into sort of quasi-equilibrium, but for deep ocean heat content processes not to start taking effect. So basically it's quite good for timescales maybe greater than 10 years and less than 50 years, which conveniently is the sort of timescale of the phenomena we're trying to address here. And the idea really is just to see if we can to get some hypotheses for how we explain these differences in terms of either the forcing, the RFF, or this climate feedback parameter alpha. And that's proved quite useful in analysing some other models. One thing that's different here, which was a surprise to me, and really I'll talk about on the next slide, is that I'm going to make this climate feedback parameter alpha. So this is like 1 over the climate sensitivity. And rather than viewing that as just a constant, I'm going to allow that to vary in time. And as you'll see from Tim's and Jonathan's work on the next slide, that turns out to be really important. So I'm just going to cut to the chase here, and there's a little bit more detail in the paper, but as I say, most of this is just hypotheses rather than detailed analysis. So let's look at the forcing first. Let's look at potential issues with the forcing. So what we've got on this right-hand plot here is the ERF due to the well-mixed greenhouse gases in red, due to the anthropogenic aerosols in blue, and then in black it's the total forcing, which includes all the natural forcings as well. And the solid lines here are from the model, and the dashed lines are the best estimates from AR5. So what you can see is, I think we kind of knew that this model has a, relative to other models at least, has a relatively high but not massively higher radiative forcing from the greenhouse gases. But the big and obvious difference is with the aerosols here. So particularly in this early 20th century period, where the aerosol forcing decreases by more than in the AR5 central estimate, and also in this 1950 to 80, where it really takes a shot down. Now, the important thing to emphasize with this, of course, is that the uncertainty in the aerosol forcing is huge. So for the end of the period minus pre-industrial, it's quoted in AR5 from something like -0.1, which is here, to about -1.9. So the chances are that the model is within the uncertainty, but the uncertainties are huge, and it's pretty clear that we are below the central estimate. And to be honest, it's really hard to think in the context of this model of any other reason why we would see these cool anomalies in those periods. So I don't think that's any surprise to anybody. I think we were expecting that. So I'm just going to kind of move on from that.
2 minutes, Richard.
Okay. Oh, yeah. Oh, hold on. Let's go back. Yeah. Okay. There we go. Okay. So the other thing you can do for alpha, I've said make this by basically regressing NT against N minus F through the run over some kind of moving window. You can diagnose alpha as a function of time. And that's what was done for some CMIP5 models in this Gregory et al. Paper. That's the black curve here. And you can see that over the historical period, the effective climate sensitivity varies by a factor of 2, actually. And then if you actually give the model the observed SSTs rather than the simulated SSTs, you get the blue curve. So again, you get very strong historic time variation. But you can see that in particular, the recent period is a period of low climate sensitivity if you give the model the correct SSTs, whereas the models are not simulating those SST patterns and so giving us higher effective climate sensitivity. And basically you find exactly the same thing in the in GC 3.1, only with somewhat higher values of the climate sensitivity. So overall the model has higher climate sensitivities, but actually if I'm looking for errors in the climate sensitivity, I'm more likely to focus on this difference in the time variation, which is a factor of 2, rather than the difference between GC3 and the CMIP5 models, which is more like a 40% difference. So to cut to the chase, as I say, the conclusion is just a hypothesis. So for the early 20th century warming, we think it is most likely to be, the anomaly is likely to be due to too strong aerosol forcing increase. Almost certainly that's true for the 50 to 80 period. And then post 1980, you can't blame the aerosol forcing. So the effective climate sensitivity is almost certainly too strong. But the most likely explanation for that is incorrect variation of this time varying component. So you cannot deduce from these, at least from this framework, that the overall climate sensitivity in the GC 3.1 model is too high. So the real conclusion is we need a lot more work to understand this. So we're just about to set up what's called a PEG, a focus group, which is looking to basically improve this historical simulation in the next generation model. And we're really hoping that we can get a lot of community involvement in this. It sort of follows up from the workshop that we had about a year ago, and sorry it's taken us a long time to really follow up from that. But we're going to set up this group and hope that we'll be able to attract some wide interest from the community into contributing to that. We've got about 2.5 years really until we have to actually decide what we're going to do for the next generation model. So really the main purpose of this talk is to encourage people, if you're interested in this problem, to get involved, and we'll be publicising this group shortly. Thanks.
Okay, thanks, Richard. In the chat, there's a question from Matt Collins. How is the ERF calculated? Is it done using your equation on slide 1 with a fixed alpha?
No, it's calculated using the constant SST with time varying forcing atmosphere only runs. Okay,
and one that's following up on that, I think, from John Bruin, is this time variation in alpha a physical process, or B, is it a simulation calibration effect? What is the impact of the variability of the ECS estimates on it being A or B? A being physical process and B being a calibration effect.
Okay. Well, I mean, you'd be best off to talk to the experts on this. But my understanding is, it's this kind of recent low climate sensitivity seems to be associated with the recent sort of IPO-like SST patterns in the Pacific. I think my understanding of what I've read of the papers is that there's still some debate about exactly what the physical mechanism is for that. So I think that's still a bit of an open question, but it's a very common across a significant number of models, including a lot of CMIP5 models.
Okay, so and I think you've answered my question there, which was what type of SSTs in the recent period are giving this low effective climate sensitivity issue. You said that, and the reasons for that are still being understood. Is that correct?
I think that's my understanding. As I say, so Tim and Jonathan are the experts on this, but there's still some debate about what's causing that.
Okay, I'm going to ask one last one, and then the others are going to have to go into the chat, I'm afraid. So from Rick Williams, is the time variation linked to changes in cloud distribution? Is there a time variation that is linked to changes in cloud distributions and feedbacks? Meaning, I guess that means, is there some kind of synchronicity between cloud feedbacks and the SST patterns?
Yeah, I believe that's the case. So there's some papers by Tim and Jonathan that talk about that. Yeah.
Okay, great. We'll go to the next talk, and the extra comments please put into the Google Doc. Okay, so the next one is by Ranjini Swaminathan from University of Reading, and she's going to tell us about some analysis of the scenario MIP simulations made by the UK system model. Okay, over to you, Ranjini.
Hello, can everyone hear me?
Yep, can hear you.
All right,
fine.
Okay, great, yeah, all right. Good morning. I'm going to talk about, work that is very much under progress about studying regional climate change at different levels of global warming in UK ESM1 scenario MIP ensemble. This is work done with colleagues at the University of Reading at the Met Office and largely driven by the UK ESM core group. So I'll just get started here. So we're looking to see how key climate variables change in terms of understanding how scenario simulations can be used to understand and prepare for impacts to humans by studying some key climate variables that around global warming threshold exceedance years. So we look at certain temperatures for global warming thresholds. That's 1.5, 2, 3, 4, and 5 over here. I'll just start off very briefly with this small plot here that explains how we actually calculate the threshold exceedance. So what you're seeing here is basically we compute the threshold years or the years of exceedance by computing a 21-year rolling mean centered at each year for global surface temperature anomalies relative to the 1850 to 1900 period. So if you look at this thing here, it kind of shows you how we calculate the year of exceedance for 1.5 and then for 2-degree warming. For ensemble means and for multi-model means, we average the anomalies and then run it through the same process and build a curve like this and see where it exceeds temperatures. So coming back to this big plot over here, we kind of see the dots are CMIP6 models and the different colors for the different SSPs, with SSP 126 being the most sustainable scenario with a lot of mitigation efforts packed in. And the 585 is the other extreme. So as we can see here, obviously the SSP 126 drops off quite early on beyond the 2-degree warming. So it was, I believe, designed to have all models not exceed 1.7 degrees of global warming surface temperature. But we already see here that CMIP6 models are tending to be warmer. This dashed line indicates that some models did not exceed the threshold for this particular SSP, and that number is 6. So 6 out of 15 models considered did not exceed the threshold. UK ESM is represented with the square and a line to express the range of UK ESM ensembles. So that's kind of here and here. So as you can see, some of the models in our analysis showed a very early exceedance. So this is the Canadian model here, and UK ESM also tends to be a little bit on the warmer side. So our analysis from here on is more focused on UK ESM, although we have plans to extend it for multi-model analysis as well. But this is just to place UK ESM in the context of other CMIP6 models. This is how we calculate the global warming threshold exceedance years. And then I'm going to talk a little bit about the different kinds of analysis we're looking at to understand the world in the future under these different threshold exceedance scenarios. So we're looking at zonal mean anomalies. So this is an example of one thing that we're looking at we're looking at surface temperature and sea ice concentration. So percentage change in sea ice concentration and surface temperature. And we can right off see that there is definitely going to be sea ice loss under, for all different thresholds. And as expected, a 4-degree warming sees more sea ice loss. We're also seeing a large Arctic amplification accompanied by this sea ice loss. And we see something similar here in the southern hemisphere as well. So one thing of interest that we're trying to look into a bit more is this kind of unique structure of like dips and highs here between, before the 80-degree north period. And that's something we're trying to understand better and see what might be going on over there. So that's one instance of a zonal means analysis that we're doing around global warming thresholds. Sorry, I'm not able to get, yeah, all right. This is changes in land surface temperatures. So we're looking at land only because we're focused on trying to drive this for policy making and to assess impacts for human life in the future. So we see that there's considerable northern hemisphere warming. And some examples to point out here are, so basically winter warming in the Alps, for example. So and we see that that could potentially, so that's about like 4 degrees under a 2-degree warming and about 6.5 for a 4-degree warming. And that could imply melting glaciers, and could mean something for the ski industry. We're also seeing quite a bit of warming in the Amazon, particularly in the 4 degree, under 4 degree thresholds, where the 4 degree threshold is exceeded. And there is also warming in the Mediterranean. And I'm going to kind of tie a little bit of this with the precipitation changes, which is coming up in the next slide. So we'll just kind of go back and forth here. I seem to have lost the arrow, the next slide key. Right, okay. So changes in precipitation. So some things that I can highlight over here. So first of all, we thresholded this data. So we removed anything that had rainfall less than 0.5 millimeters per day. And again, just to reiterate, and I'm not sure if I made this clear, but we're looking at 20-year averages around the years of threshold exceedance, and we're looking at the anomalies compared to the 1850 to 1900 period to look at the change. So the stippling here indicates regions that we didn't consider because of very low rainfall, so that's less than 0.5 millimeters a day. But some things to highlight here is a reduction in rainfall in the Amazon, and that coupled with warmer temperatures there could mean that the P minus E, the precipitation minus evaporation values will also show us that the drying there, and this could potentially mean something for the vegetation and then for the carbon uptake of the Amazon in the future. So these are some things that we want to kind of look into. Yeah, this is my last slide. Yeah, these are some things that we want to really dig into, and really we're going to look into higher temporal and spatial resolutions for this, but we're starting off with getting like a high level picture and kind of zoom into regions that we think are more impactful to study. What are some other things? So we also see that the Indian monsoon, so that's basically rainfall in India in the JJA, the monsoon period, sees an increase from about 30% in the 2 degrees Celsius to about 70% here. But this is not accompanied by an equivalent temperature increase, so which means that maybe the precipitation is keeping the temperatures down. So there seems to be an increase in rainfall in the near the Sahel region as well. And in the Mediterranean, we see a drying of about 20%. So that coupled with the increase in temperature could mean that that area becomes hard to live in the future, and that's something that might be of concern, that will be of concern for the future. So I'm going to stop here and just say that this is definitely work in progress, and we're trying to highlight some areas that we can dig into and really do some analysis with the scenario MIP ensemble in the next few months and year or so. I will stop here and take any questions.
Okay, thanks, Ranjini. You can hear me okay?
Hello?
Can you hear me?
Yes, yes.
You can, okay. Okay, so question from Jeremy. It looks like a very large increase in rainfall, 4 degrees in Eastern Europe and Russia in DJF. Yeah,
Yes.
So in the northern hemisphere land regions. Can you comment as to why that might be? Remembering, I guess these are percent changes.
Right, these are percent changes, yes. So I should mention that. So this is percent changes with reference to the 1850 to 1900 time period. I don't know why that might be, but that's something that we will look into. Like I said, that's one of the things we're going to, so I'm basically just highlighting things that have cropped up as interesting that we should probably look into and see why. And that's one thing we will look into, yes. Sorry, okay. I had that on my notes as well, and I didn't raise that up, but yes, that's one of the things I wanted to highlight as well.
And Kath is asking, so I should stress, because I'm involved in this, this is early days with this work, so
Yes.
probably the answer is no, Kath, but I'll ask it anyway. Have you
No.
looked at the linearity of the response between 2 and 4 degrees?
No, we
Meaning,
haven't, but yeah, that should be something interesting to look at. Yeah.
Right.
Yes.
Yeah. So does 4 minus 2 look the same as 2 minus
2 minus. Yeah.
pre-industrial? Yeah.
Yes. Yeah.
That's definitely something we do want to look at. Yeah.
Yes. Yeah. That's a good thing.
One further question from Yevgeny. Sorry if I missed this. Is this solid or liquid precipitation, or both together?
Both together.
Is it rain, snow, or both together? Both together.
Both together. Yeah.
Okay, and I agree with Yevgeny's implicit comment that it may be worth us considering looking at changes in snow, because
yes, changes.
you could get neutral precipitation, but a switch from snow to rain. It's true.
This is both together, but yes.
Yep. Okay, many thanks, Ranjini.
All right.
All the questions. If there's any more, please dump them into the Google Doc, and we shall go next to T. Taraka, or T. Davies-Barnard. And T, I haven't got your...
Thanks.
So, yeah, I thought it would be about nitrogen. So I think so. T is going to tell us about nitrogen in the Earth system. Over to you, T.
Hi, my name's T. I'm from University of Exeter, and I'm sorry for my absence in this whole thing. I don't seem to have gotten any of the emails, which I don't know why. Anyway, this, if I can figure out how to click on, which, aha, yes. So this is a slightly different format talk, because we all need some kind of joy in our lives at the moment. So I encourage you to play along in the group chat. And you know, it's not like a test, like you don't have to get all the right answers. The point is for it to be a bit of a fun way to talk about the nitrogen cycle and what I've been doing with Crescendo. So this is sort of T's lockdown biological nitrogen fixation quiz. So question 1. Which I now can't see because I've got the things in the wrong way. But anyway, what is BNF and how does it fit into the terrestrial carbon and nitrogen cycle? Is nitrogen either an essential nutrient for plant growth and carbon uptake, and the main source of natural nitrogen to the terrestrial system, and that it's important because it will potentially limit the amount of atmospheric carbon dioxide that can be taken up by plants in the future, or it might be its nodulated fixation on legumes and other plants in symbiotic relationships, and it comes from fixing bacteria and it's highest in the tropics, or it might just be the next thing on the list that we need because, you know, CLM have it. Yeah, if you want to play along, pop your answer in the comment, and we'll go on to the answer, and which is of course A. Of course, it's nothing to do with keeping up with CLM. It's that that it's a really critical part of the carbon nitrogen cycle. And it comes from a range of different sources, and it's not necessarily highest in the tropics. So although when we think about biological nitrogen fixation, you might have heard of clover or, you know, these sorts of things, but actually it happens in a lot of different places with a lot of different processes. And so it's very, very heterogeneously distributed, and it's therefore quite difficult to model because it's, it has a lot of different processes associated with it. And it's really important because especially in nitrogen limited areas, it potentially can limit the amount of carbon that could be taken up by plants in the future. So that's the sort of basics of what it is. So the next question is, how do models commonly do this? Model biological nitrogen fixation, and you've got 3 options. You've got a linear relationship with evapotranspiration, you've got a linear relationship with NPP, or you've got something else, we'll say. Thank you to Colin, who appreciated my joke, which, yeah. So everybody got their ideas in line. So although all are good answers, actually NPP is the most common way of modeling biological nitrogen fixation. Basically, this is all down to a paper some years ago that showed that there was a very strong linear relationship between biological nitrogen fixation and both NPP and evapotranspiration at a global scale. There were, that has now been superseded by subsequent analysis done by me, which shows that actually there is no relationship between BNF and NPP or ET. It's not a great relationship at all. So, yeah, no, you're right. It's a vegan cheeseburger. Sorry. Yes, vegan cheeseburgers. So it's not a great relationship, and so it's tricky to say what we should do instead, because it's really difficult to see what is a good relationship because it's so heterogeneous, and it's quite a complicated process. So the next question is, what is the present day range of BNF in system models, or their land surface model components? Oh no, is that actually the question? Sorry. Yeah. Oh, I appear to have, okay, I have full disclosure here. I may have messed this up because I had to adapt it to be only 4 slides in order to have it the same talk for EGU and for this, and I appear to have messed this up completely. So we'll go with the answers being correct rather than the stated question. And so the question is not what's written, but why is it important that we get the right relationship between BNF and whatever we're modeling it with? And so that's the question, and the potential answers are either because each part of the model really matters, and if you get and it's a cumulative sort of process of getting everything right, each small component right, in order to get everything right, or because the amount of BNF, being the largest source of nitrogen into the system, can really affect our amount of future carbon uptakes, and so it's policy relevant, or because correlation is not causation, and just basically fundamentally we should get this right, or all of the above. And
2 minutes.
Oh, sorry, I'm right. We're on the last slide. So, of course, it's the answer is D. It's all of the above. So I've just got a small bit of results here from the model, some of the models that we looked at for in the Crescendo project, and we can see that this is the change in BNF over between 1950 to 2005, and we can see that there's a big range of changes over that historical period. You have to believe me with the units that it's a very wide range, but particularly you can see that some of them are negative and some of them are positive, and that really matters because that's basically providing nitrogen to the system. And this is all tied up with the assumptions. In particular, LPJ gas works off evapotranspiration, and because evapotranspiration very slightly goes down in that model scenario, so does the BNF. But as we've seen, there's not actually a real relationship between ET and BNF. So in summary, this is clearly work that is not yet finished, But it does matter, and it could make a difference. And there's some there's work on both the modeling side and the data side to improve both aspects. And I'm on email if you want to chat. And thank you for humoring me. And if you have any questions.
Okay. Yep, can you hear me, T?
Yes.
Right, thanks for the quiz. I don't know about, so cheeseburgers was obviously the right answer because it's always the right answer.
Always.
Yeah, so if there are any questions, they're coming in the chat. I shall begin. So one of the issues with nitrogen is obviously constraining it with observations and knowing what the target is. So can you say something about how these nitrogen schemes are constrained in any way, either directly or indirectly by observations?
So I suppose I can speak for the BNF part of it, and the answer is not very well. Up until now, all we've had really to work off in terms of the constraint is a maybe 20-year-old meta-analysis. And so that's one of the things that actually I started doing when I worked with Crescendo, was I was tasked with improving the BNF within the model within Joules. And my first question was, well, what would that look like anyway? And the answer is we still don't really know. So after a large meta-analysis, what we've come out with is a very large range of potential present day BNF. And there is some studies that show, you know, what BNF does under elevated CO2 and things like that, but it's still not a very straightforward issue because we don't really have the data, as much data as we would really like. And yes, I think that's the short answer. There's not as much data as we'd really like.
Okay, and there's a question from Zhijiang. How are other processes such as nitrification, denitrification represented in our system models?
It depends on the model. There's a variety of very sophisticated to quite simple representations. Some models, these processes are basically just taps that you can turn on and off and tune quite heavily, and others have a lot more, I hesitate to say process-based, but process-based evidence behind them. Again, there's not as much data to compare it against as you'd like. There's a couple of good papers around exactly how those processes work, which if you send me an email, I'll pass on the links or the papers.
Okay, last question. So we're referring here to the nitrogen cycle, but I think it's fair to say in most models that is primarily just a land-based nitrogen cycle. So how important for these models is it to have nitrogen activity and exchanges between the marine sector, the atmosphere and the land, so we have a more complete nitrogen cycle? Is that important, or is it enough just to have the land component? I
mean, the ocean's really important, but most of us live on the land. So to some extent, I mean, I'm probably partial here. But and I don't know that much about the nitrogen cycle in the ocean. However, we do know that what humans are doing generally is a massive experiment in adding nitrogen to absolutely everything, in particular to land, and then it gets into the water and you get eutrophication in rivers, and then that will eventually get to the sea and you get eutrophication in coastal shelf areas. How important that is for the deep ocean and for the, you know, for the larger part of the ocean, I don't actually know. I mean, fundamentally, yes, of course you want a joined up system, but not at the expense of making it impossibly heavy to run. So yeah, I think in an ideal world, yes, we would like a joined up system, but in reality, we might decide that actually until we can get the get computer power that can actually make that, somebody's just said that there's the long timescales for the deep ocean as well, which is an issue. On the land, we're talking about really quite short timescales, especially because nitrogen leaches so much. We're talking about days, months, years, whereas for the ocean, we're talking about much longer timescales potentially. So yeah, I don't really know. There you go. I'm not really sure. I think in an ideal world we would.
Okay, and there's a comment from Rick Williams about a paper by Vivek Aurora around this topic. So you can see
Yeah,
that.
no, I've heard of him.
I think you know Vivek anyway.
Yeah.
Okay. I'm going to have to wrap things up now so that we stay nominally to time. So many thanks, T. There's a few comments in the chat that you can see, and otherwise, hopefully in the Google Docs. Right, I think that means we are done, and I believe this is the final UK CMIP6 analysis session. That's correct, isn't it, Hazel?
That's right, yes.
Yeah. So, whilst we can't applaud, I would like to thank Hazel and Poppy, who have been doing all the administrative and organisational side of this, and it's taken a fair amount of work. And I think this has run really well, actually, given the circumstances. So, many thanks to Hazel and Poppy, and many thanks to the presenters today and the presenters earlier on. And hopefully, by the time we have a 2021 or 2022 UK CMIP6 analysis workshop, or at least the UK CMIP7 analysis workshop, it could be that we're having it in person. So with that, I'm going to stay safe and enjoy the weekend. Thank you. Bye.